Audience, we're about to get started again. I'm Rick Bernhardt, and once again, I'm the Scientific Support Unit Manager at the Department of Environmental Conservation. What I tried to do with this presentation is really address the common themes from the public comments we got when we did our initial dispersant outreach back in 2013. As was mentioned earlier, we're actually right here in Alaska, and gave a presentation in this very same room. And after that effort in 2013, we got around 500 just public comments and another 300 comments from federally recognized tribes. And there were, as you guessed, there were a lot of commonalities in those concerns, with some differences. So what I tried to do is to dip into the scientific literature and sort of address those common themes based on the scientific publications. Now, I want to qualify this though that if you do a search in an academic search engine on dispersants between the time frame of the Exxon Valdez oil spill and the Deepwater Horizon, you're going to get about 37,000 published peer-reviewed scientific publications. I'm not going to cover all those in the next 35 minutes.
Oh, good.
And Catherine keeps me honest and humble. I often go into 40 minutes and she sets me straight. But if you were also to go, and just do a Google search for dispersants in that same time frame, you're going to get up 93,000, just papers in the gray literature. So there's quite a bit known. There's quite a bit of conversation that's out there on dispersants. It's a hot topic. So very briefly, we're going to talk a little bit about the scientific method. We are going to talk about some of the publications that tell us what we know. I'll give you a glimpse into how we know what we know. We'll look at a few of the facilities where research is done. We'll talk about some toxicology, some functional norms, and then we're going to wrap it up by talking about, based on what we know through the scientific literature, what can we do about that? How many of these effects can we mitigate through wise use of policy? So we prefer to gain our knowledge with controlled scientific studies in laboratories. We prefer not to have a spill and then have academia descend en masse and try to characterize what effects have happened and what long-term effects. But when you're working with beakers and flasks and jars, there's only so much realism you can pack into that. You can imagine right here in Captain's Bay, the environmental conditions in May are going to be a heck of a lot different than they're going to be in August. And only one of those factors depend on your temperature. You could have other factors, for example, how much runoff do you get? It can affect the salinity. Of course, you look at the species that are here in warmer temperatures, and that's going to differ from those here that are here in colder temperatures to some degree. So when you're trying to replicate nature in a lab, there are some obvious limitations there. But of course, we don't just rely on research that's done in the lab. There are some other facilities we'll talk about that I'll call them mesocosm experiments, but one facility actually has a tank that's 2.6 million gallons large. In New London, Connecticut, the Coast Guard operates a research and development facility. We were fortunate to have one of the leading research managers come in and talk to us right here in Alaska this last April. And then there are a number of countries who still do real oil releases on purpose for scientific research. Norway is among one of the leading countries that's most active right now. In fact, just this last summer in July, they had a controlled release in the North Sea, and we actually had some Americans who went to participate in that. And like I said, when large spills happen, academia does descend en masse to study what immediate effects and also what long-term consequences there are from spills. And those are our least favorite types of ways to learn information, but they do provide exceptionally realistic results. And I will go in a little detail later on to look at how well can we translate what we learn in the lab to what we actually observe when we do controlled releases or when there are less controlled releases. Now, one thing I want to mention about the scientific method, it was neat to hear that we have a lot of environmental managers, we have a lot of biologists, we have a lot of, I think, scientists from the community in the room. And so I think I'm not talking to an uneducated audience about the scientific method, so I'll keep this fairly brief. But of course, when you go to, when you do research in academia and you're ready to publish, generally there's a team of people who have done the research. It's exceptionally rare nowadays to have a single author on a peer-reviewed publication. So you have a team of collaborators, you design your control study, you have certain variables that you'll manipulate, and then you make your measurements, you determine how well your results support or refute your hypothesis, and you attempt to publish. Once you've written your paper and you've submitted it to a scientific journal, you're going to be assigned at least 3 subject matter experts in your field where you're publishing. And they're going to criticize your paper in an attempt to improve it. They're going to say what they feel are the weaknesses. They're going to challenge certain results or certain methods. And if your methods weren't rigorous enough to confirm a finding, you may never get published. What happens more often is you get that constructive criticism back, and you'll revise your paper and you'll resubmit. And that process can last over a year, depending on the intensity of those changes. And then once you did get the green light and you're able to publish, now you put it out there for the world scientists to see. And occasionally there is a little drama within the journal that you published in. Sometimes that'll result in a paper actually being pulled back. I'm missing the word there, but retracted. Thank you very much. Yeah, absolutely. Sometimes it'll cause that. Sometimes it will cause the authors to come back and basically qualify their report and correct it. But that also opens the door for other researchers to replicate your results or disprove them. So I'm going to dip a little bit into some of the fundamental properties of really every liquid, but it's most relevant here with oil when we're talking about how well will it disperse, how well will it sink, or how well will it diffuse into the water column. So the first important property is the specific density. Again, every liquid has a specific density assigned to it, and what that does is it's a comparison of that liquid's property in comparison to the density of water. And so any substance that has a specific density greater than 1 is going to sink in the water column. Anything with a specific density less than 1 is going to float. It's a fundamental chemical property. And if we look at Alaska North Slope crude oil, the specific density is between 0.88 and 0.93, suggesting it has a tendency to float. Next we'll look at the pour point. And the pour point, basically, there's a manual method for testing this. You can put a liquid in a beaker and you turn it on its side, and if it flows out of that beaker within 5 seconds, you say that it's liquid and it's above the pour point. You'd hold it there for 5 seconds, and if it doesn't flow out of the beaker, you raise the temperature 3 degrees Celsius and you try it again. It's not, it's not such a tough concept, but if you're below the pour point, that substance is going to be less inclined to mix into the water column, and it's also harder to disperse. So if we look at the pour point of Alaska North Slope crude oil, it's negative 8 degrees Celsius. So pretty much everywhere in Alaska, if you're dealing with liquid water, you're going to have Alaska North Slope crude oil in liquid form. Viscosity. So you guys, know the concept of viscosity. Your liquids that flow less easily. You're going to be, have a greater viscosity. And basically, the important point on this one is that temperature can affect viscosity, of course. So in the wintertime, when the temperatures are lower, viscosity of crude oil would be higher, and so it's less likely to be dispersible, and it's less likely to mix into the water column. Now, the thing about dispersion, we talk about dispersants and dispersing oil with dispersants, but the thing is, oil will disperse, period, naturally. As Catherine mentioned, there's a water-accommodated fraction. Sometimes we talk about a breaking wave water-accommodated fraction. We talk about chemically enhanced water-accommodated fractions. And what that says is basically when there's very low energy, when there's very low mixing energy in a body of water, you're going to have less of those soluble fractions, less of those soluble chemicals in crude oil that are going to get into the water column. But they're going to get in, with or without dispersants. When you increase the energy in the water body, you're going to have more of those chemicals. And I'll give you a little bit of frame of reference. On a nice calm day with a very mild breeze, I'm not going to throw numbers at you, but you'll get a certain fraction that disperses into the water column. When you increase the wind energy and you have a sea state in the Beaufort scale about 2 to 3, you're going to have about 5 times more of those soluble fractions that get into the water column. You'll also have some of those larger molecules that begin to disperse into the water column. That's without adding dispersants. Now you add dispersants in the same condition, you're going to get about 50 times more. So it's extremely effective if your goal is to disperse that oil into the water column. When you add dispersants, you're also going to get a different fraction, different chemicals into the water column. You'll get more of those larger molecules. And generally, what happens, if you look at Alaska North Slope crude oil, if you just have natural dispersion, you're going to get a lot of those smallest molecules that naturally dissolve into the water column. The larger molecules are more hydrophobic. They just don't have a tendency to get into the water column. But when you add dispersants, as Catherine mentioned, you're going to coat those molecules. And you're going to have basically the same proportion of those larger molecules in the water column as you do in your source oil. That's what happens. Now there's a trump card on this. It's called sedimentation and adherence. So when you're in, especially the nearshore area, and you have a lot of organic molecules in the water column, they'll bind to that oil, and they can change the density. If you're right at the edge of a turbulent river mouth, maybe you're kicking up some sand. That can adhere to the water droplets, or to the oil droplets as well. And when you throw dispersants aside, when you're just looking at those chemical properties, when you have things like sand that adhere to those oil droplets, it's going to sink, and it may get well down below the 10-meter magic line that we often reference. So I guess my point is there are some natural factors out there that can really change the properties of oil. It's going to change how well that oil gets down into the water column, and under special circumstances, oil, with or without dispersants, may make it all the way down to the bottom. Go ahead, Chris.
So on that, I was just curious, so if it's dispersing equally within the water column, you wouldn't have oil settling on the bottom. That was my question. Is oil going to settle on the bottom?
In general, no. But I did want to throw out this one qualifier, that when you have mixing in turbulent areas with a lot of sedimentation, or you get special circumstances where oil adheres to sand, a portion of it could go to the bottom. And that's with or without dispersants. That's just a physical
So as sand's mixing up, it collects on the sand and settles
It
the sand?
can.
The sand settle.
Yep, it would follow the sand because it's changed in density. In general, you don't have that equal distribution. We're going to go into that a little bit in a few moments. But in general, that oil is going to have the highest concentration right near the surface, And the deeper you go, the less the concentration is, the less oil will make it deep. And in general, it won't go below about 30 feet or 10 meters. And I just wanted to point out that there is a trump card, there's an exception. And so I don't want anybody to get the wrong message that, I'm saying it doesn't happen. There can be exceptions. So I like this picture quite a bit. This is the primary test facility in the U.S. This is at Olmsted in Leonardo, New Jersey. That tank is a little over 600 feet long. It's about 60 feet wide and about 10 feet deep. It's got windows on the side. It's got a wave tank in there. You can control a lot of things. And this is the tank where I was saying, when we do dispersant research, we can fill it with about 2.6 million gallons of Atlantic seawater. We can manipulate the temperature. And just this last year, the Bureau of Safety and Environmental Enforcement, BSEE, just published results of their dispersant tests at this facility. And what they did is they looked at 4 different dispersants, and they had a control group. So you have 4 treatment groups and a control group. And their goal was to find out which dispersants would be most effective on Alaskan North Slope crude oil, on Alaskan oil. I misspoke a little bit because what they used was a blend of Alaskan North Slope crude oil and Cook Inlet oil, Cook Inlet crude oil. So all of it's Alaskan, but it's not 100% Alaskan North Slope crude oil. Now, scientific publications don't rely on a single test and a single observation. If you can't replicate your results, you might as well be doing philosophy. It doesn't mean anything. Well, that was an overstatement. Sorry, I hope there are no philosophers in here. But you have to be able to replicate your results. And you have to be able to say, statistically, here's a pattern. So what they did in this group, with your 4 treatment groups and your control group, is they had 3 replicates per treatment. And they would expose this blend of oil, this blend of crude oil, to one dispersant at a time. They would run a test for 20 minutes, and at the end of that 20 minutes, they'd take a measurement. They'd find out how successful that dispersant was to disperse the crude oil. And what's great about this study is really the water temperature there. The water temperature, the surface water temperature is between 26 and 32 degrees Fahrenheit. So you look at the Beaufort Sea or the Chukchi Sea, and in general, during the ice-free season, the temperature is between 0 and 5 Celsius. That's 32 to 41 degrees Fahrenheit. So these are environmentally relevant conditions there with the surface water temperature. Also, I mentioned that at Olmsted's test tank, there's also this spray bar. And what it does is it basically can run the length of the tank, and it can aerosolize your dispersant. So they ran these tests for 20 minutes, and they kicked in the wave tank, and every 4th or 6th wave was a breaking wave. And here's what we found. On the bottom, I'm on slide 6 for the phone audience. But the bottom row highlights the control treatment in green. So all of these other tests compare a specific dispersant to the controls. What they found was Corexit 9500 performed the best. Its median droplet size was a little over 83 microns. So the magic number we're looking for here is 70 microns. If a droplet size is 70 microns or smaller, it'll stay dispersed into the water column. Droplet sizes larger than 70 microns will resurface. So what you notice here, the best performing dispersant had a median droplet size of 83 microns, larger than that magic number of 70 microns. It suggests that the majority of those droplets are going to resurface. I'm going to circle back to that in a second. But after 20 minutes, almost 73% of the surface oil had dispersed into the water column. Now, any scientific publication will describe the results of whatever's being tested, given certain parameters, and every publication will describe what those parameters are. So the limitation here, these tests will only run for 20 minutes. If the median droplet size is 83 microns, and they're saying that there's a 73% effectiveness, what's not being said is that you would expect some of that to resurface. So if you were to take these measurements an hour after the test was run, that mean effectiveness would go down. Now, we have some other data that suggest a longer term effectiveness might be somewhere in the range of 30%, perhaps even 40%, depending on what dispersant you're using. So this is exceptionally optimistic, but it is giving an accurate characterization after 20 minutes. Correction 9500 did the best. Phenosol OSR 52, that one was proposed to bring to Alaska, but those plans were scrapped when Shell decided not to continue their exploration in the Gulf of Chukchi. If you look down here, now this ZI 400, that's a water-based dispersant. All of these other dispersants that were tested use a base of oil distillates, so they're more effective at mixing with oil. But this ZI 400, look at the percent improvement over the control. It actually has a negative improvement. It actually did worse than the control. And one of the problems was that water-based dispersant was actually freezing in the nozzles of that spray bar. But you're not going to get your money's worth if you're buying ZI 400. I should mention Corexit 9500A is the only dispersant here in Alaska. And as you can see from these results, that's the most effective dispersant on Alaska North Slope crude oil and Cook Inlet blend. So we have the right dispersant here in the state. This is the oldest paper that I'm going to talk about today. It was actually published in 1985, and it characterizes the results of 54 other publications. It's a review paper. And it talks about functional norms, and basically one of the functional norms is that the polynuclear aromatic hydrocarbons, the PAH concentration is much higher when you're using a dispersant than when you're not using a dispersant. Again, it has a similar proportion to the source oil. If the source oil has 30% PAHs, your water column is going to have about 30% PAHs when you're using dispersants. When you're not using dispersants, those larger molecules, those bigger PAHs, aren't going to get down into the water column quite as effectively. Again, dispersants, the oil will typically stay in the top 10 meters of the water column. They'll have the greatest concentrations right by the surface, and as you descend in depth, the concentration is going to get smaller and smaller and smaller. But generally, that oil will stay within the top 10 meters. Now that's if you have great energy. That's if you have a lot of motion, rough seas. If you have calmer seas, you're not going to be nearly as effective. But in that upper 10 meters, in general, you're going to have about 10 milligrams per liter 1 meter below the surface. Depending on that mixing energy, it may get as high as 150 milligrams per liter. What does that mean? These are big numbers. Maybe they're not big numbers, I don't know. What it means, these numbers are actually 1 million times to 150 million times the level at which we've determined is toxic to the most sensitive life stages of fish. If you're down about 1 nanogram per milliliter, 1 million times smaller than these numbers, if you expose an organism at the most sensitive stage in their life, right after fertilization, these numbers are way more toxic than that. So as Catherine mentioned, it is a trade-off. You can't just say that here's a condition and it's going to be great in every circumstance. You have to look at other variables, like what's the season, what organisms are in the area, before you can decide, are dispersants a good tool in this situation, or are they not? And that's where wise policy comes in. So a couple other conclusions. I failed to mention, but these are the functional norms based on real field tests. One of the things that we've determined is that the optimal dispersant to oil ratio is 1 to 20. One part dispersant to 20 parts oil. They've tried ranges as much as 1 part dispersant to 1 part oil, and they've had it as dilute as 1 part dispersant to 67 parts oil. And what we've settled on is 1 to 20 is the optimal ratio. Now here's the kicker. About 90% of the slick lies within, 90% of the oil lies within about 10% of the slick. So you can't just set your nozzle on your plane to disperse at a certain volume. You have to be able to adjust how much dispersant is coming out of those nozzles. Because again, there are thick areas within this slick, and as you get out on the margins, there's a lot thinner. So you have to be able to adjust those ratios. And what we found is that applying dispersants from the air is a heck of a lot more effective than applying dispersants from a boat. And some of that's because there's this bow wave that's constantly pushing water out. You don't get good exposure. But another part of that is it's your angle of view. When you're up higher, you can see, you can actually determine, you can distinguish the thick areas of oil from the thinner areas of oil, and you can adjust accordingly. There have been instances where dispersants have actually missed the slick when they're applied by boat, because the boat captain, the vessel master, can't see the different thicknesses, the margins when they're down low. Sir, you asked a question earlier about how long the dispersant's been used. The first technologies came about in around the 70s. And this Corexit 9527 was one of those early batches, and we found that it was a lot more harmful to the environment. And in fact, the Corexit 9527 isn't being made anymore. They've gone exclusively to 9500, the one we have in Alaska. A lot less harmful to the environment. You saw Catherine's graph that showed the LC50 curves with 9527 having a lower LC50 than 9500. But in other countries, what Catherine said was absolutely right. In the U.S., we don't use dispersants very often at all. The last time was in Deepwater Horizon 2010. In other countries, especially in Asia, it is the go-to response mechanism. I have some videos where it just shows dispersants being used, and it's not like we should follow anybody else just because they swear by it, but it is the go-to response. So I think there's quite a bit more known based on studies in other countries, particularly like Norway, where they're controlled studies. Dispersants are also a lot less effective on fuels like heavy fuel oil. It's those larger molecules that don't get into the water column quite as effectively. And they would be effective on the refined products like gasoline or diesel, but those are also very short-lived, and so they generally volatilize a lot quicker than crude oil. And so there's no need to use dispersants on those kind of things in general. And that's why we put those decisions in the case-by-case basis. There have to be really unusual circumstances to use dispersants on refined product. Okay, one of our more sensitive species are herring. There's a study that was done on Atlantic herring, and it's pretty typical of what you'll find when you look at the toxicity on any fish species at least. What you find, the gametes, the sperm and eggs, are perhaps the most sensitive. I'll call them a life stage, although gametes aren't alive. But what happens is when that crude oil is exposed to those gametes, they'll become infertile very quickly. Right after the gamete stage, right after fertilization, that's the next most sensitive life stage. So you have those eggs that are extremely vulnerable, and what happens is a large percentage of those eggs that are exposed to crude oil will never hatch. The embryo may not even develop. Those that do often have developmental abnormalities. there's a suite of abnormalities that's typically measured. The suite is called blue sac disease. And what's measured is heart formation. They actually measure this, the skeletal system. They measure actually the part of the lower jaw. And then there's also some developmental or abnormalities that you can measure on the spine. And what they find is that immediately after fertilization, you have an extremely sensitive stage where that embryo is very vulnerable. Usually within an hour of fertilization, the outer shell on an egg begins to harden. That's called the chorion, and it becomes more impermeable to chemicals. Water can flow through, but chemicals not so much. It's that classic semi-permeable membrane. And so you get a degree of resistance until the egg hatches. And then as soon as that egg hatches, the larvae is extremely sensitive once again. So there's a couple of stages there where it's extremely sensitive, but quickly after hatching, within a number of days to weeks, the larvae develops more resistance to oil exposure. And what we find is that the exposure